Welcome to the class of Calculus 3. In this video, we are going to study section 2.2, vectors in the three-dimensional space. First, we take a quick look at what we mean by a three-dimensional space. Simpler put, I just want to say, in the three-dimensional space, it is represented by an ordered triple, and vice versa. Ordered triple, it is for a point. And then how do we represent an ordered point? Ordered triple, a point. And then from that part, what we need to see here is the arrangement of the three-dimensional rectangular coordinate system. How about let's just take a quick look at the arrangement here. And I'll look at this case. This is the x-axis, y-axis, z-axis. Be careful about the order or the orientation of x, y, and z. Basically, x, y, and z will have to be ordered in the counterclockwise direction. Or indeed, to say it more accurately, you see the figure to the right, and there is so-called right hand rule. Okay, you use your right hand and try to fold your fingers, use your fingers pointing to the x-axis, and then fold your fingers and try to move x-axis to the direction of the y-axis. And then in that way, well, try to show my right hand here. Actually, this is the way. Use your fingers pointing to the x-axis, and then fold the fingers to the y-axis. And then in that case, your thumb must pointing upward, right? And then the thumb, it is pointing to the direction of z-axis. I would say for our class purpose, it might be very helpful if you consider this is the only arrangement we may have for the three-dimensional space. I mean, do not make any changes, especially do not switch x-axis and y-axis. Okay, this is how we draw the three-dimensional space on a plane x, y, z using the right-hand rule. Three-dimensional space. A point is an ordered triple. An ordered triple, it is a point. First component is the so-called x-axis, this part of the line segment, and the y-axis, the point on the y-axis, and z-axis, the coordinate. Okay, x coordinate, y coordinate, z coordinate. I suppose these are pretty easy things, right? So I'm not going to go through all the details. And also in the three-dimensional space, many times, I think the point, it is the very simple case. And many times we need to consider curves and planes. So how about this moment, let's take a quick look. What are the planes we may have? In the XYZ space, we may have the XZ plane, like here, the XY plane, and the YZ plane. And you must know all those planes very well. And then I say it's in the XY plane, in the two-dimensional space, the XY rectangular coordinate system separates the entire plane into 4 quadrants. And now, I believe in the XYZ space, you count, there are 8 octants. The first octant, and then the second octant, and so forth, and then move like that. And I'm going to say it may look very complicated, but anyway, if you see the idea, it should be a very simple thing. And the distance formula in the two-dimensional space, then in the three-dimensional space, accordingly, really, it is still from the famous Pythagorean theorem. The distance between 2 points. And also, I believe we need to consider the midpoint formula. I guess the textbook didn't mention here, but anyway, the midpoint formula, it is on my notes. Okay, if I see it on the textbook, I will take a look about the midpoint formula too. The distance in space, I guess it should be a lot easier to see, right? Point 1, point 2, and then we find out distance. it is the square root of sum of squares of the difference of the corresponding components. That's the distance formula. I guess there's really not a lot to say here. And also, I think this is very interesting. In the two-dimensional plane, we say two lines either intersect or they are parallel. And you need in the three-dimensional space, it's getting a little more complicated. Two lines, like those two lines, they really don't intersect. But anyway, clearly they are not parallel lines, right? We will look at lines. We do have another section, mostly the section it is entirely for the case of lines in the three-dimensional space. So three-dimensional space is a little more complicated. And then, do we have more things? I think these things are very simple things. Oh, yeah, actually this is the thing I really want to show a little more. The equation of sphere, and the sphere, it could be considered as the collection of points in the space such that the distance from each point to a fixed one, the center, is a constant. So the collection of all those points will tend to be a sphere, right? It's not only a circle. So according to the description, the collection of points such that the distances, okay, or the sign, and then we have a sphere. So accordingly, the equation of a sphere, it is generated as, well, it is generated from the distance formula. If you think very carefully, ABC they form the coordinates for the center. X, Y, Z could be of any points. But anyway, we said the sphere really, it is the distance, the collection of the points such that the distance is a constant. It is exactly the situation from the distance formula. And then we have a constant. And the constant, it is considered radius squared. So I think this one should be fine, right? I'm not going to solve this one. And you can, well, this is the solution on the textbook. The other problem might worth a little more explanation. It is example 2.15. Find the equation of sphere. We are having 2 points, P and Q. And actually this time, what we are given here is P and Q are supposed to be the diameter of the sphere. And then the question is, how do we write out the equation of the sphere? And partly the reason I'm using this textbook directly, I'm saying it's the graph. It's very hard for me to draw the graph on the computer. But using the textbook, it does have a very nice graph here, okay? First of all, think about the sphere. We need to know the center, right? And looking at the drawing, would it make sense to you? P and Q, they are forming the diameter. So the point in the middle must be the center, right? And so we need to calculate the point in the middle, okay? That is the center. And also we need to calculate the radius. The radius, there are different ways. You can calculate the length of the diameter, then take half of the diameter, that is the length. Also, if you already got the center, can I say from the center to the point P, or from the center to point Q, that also will form the radius y. So indeed, we can answer this problem perfectly. So let's take a quick look at the solution on the textbook. Okay, the point in the middle, actually, I do have the formula for the middle point on my notes. And basically, it just says the coordinates of the point in the middle, it is the average. They are the average of coordinates. So we are having P and Q, the middle point, X component, it is the average of X components. Y component, it is the average of Y's. And Z component, it is the average of Z. So the center turns out to be the order of the triple, -1, 3, and 1. And also, well, the textbook, it is calculating the diameter directly because we are having P and Q, we can calculate the length and take half of it. And also, I want to say it might be better if you often know in the center, you may want to use the center to calculate the radius. Well, I'm saying it's going to, well, because mostly it is harder to handle with bigger numbers. Hopefully, using the radius directly, we are making the numbers smaller. Okay, but anyway, let's follow the textbook. The textbook basically calculate the length of the diameter directly, and then radius, it is 1/2 of the diameter. So that is square root of 21, square root of 21. And then the equation of the sphere, it is according to the arrangement. Right here, this is the equation of the sphere, A, B, C, they form the center, R is the radius. So as the final answer for this example, we are having the equations of the sphere just like such. Hey, how about let's take a break, and I want to thank you for watching. See you next time.